Hello and welcome back. So today we're going to be looking at day 14 of Advent of Code 2019. I know that I'm skipping day 12. Don't worry, I'll come back to it. I just wanted to do day 14 because I think that this problem is especially amenable to an array-based solution. And I'm just going to give you a spoiler here. The solution that we're going to come up with for this is significantly faster than a lot of other solutions that I've seen posted in Reddit, even in lower level languages like C or Rust or what have you. And the great thing about this is that I have seen, just looking at the different solutions that I've seen posted, I've seen a lot of different data structures used to solve this problem. You have, trees, graphs, hash tables, obviously, queues. I saw one that used like a priority queue. And I think that this problem is great because it shows that just basically like by taking the sort of simple array solution, not adding these extra data structures, by operating at like a relatively low level of abstraction, the problem is actually pretty simple once you get your data into the right format, and it's highly performant as well because you're doing these type of simple array operations, matrix math, that type of thing. So I think that it really plays to APL's strengths. But yeah, so without further ado, we can sort of get into the problem. So day 14 is, you can read the description on your own, but basically it's like, I don't know if you've ever played like Minecraft or Factorio. Maybe Factorio is a better example. So the goal of Factorio is to launch a satellite at the end of the game. But in order to construct that satellite, you have to construct a whole ton of intermediate components. And so you have these recipes, and this is referenced here. You can see like, okay, in order to make one fuel, we need 7 A components and 1 E component. Okay. But then in order to build an A component, we have a recipe that gives us 10 of them, but requires 10 ore. And then in order to build an E component, we have a recipe that requires, again, 7 A components, but 1 D component. So the problem input is basically going to be a list of these recipes or reactions. And the question, if I scroll down to the bottom here, is basically what is the minimum amount of ore required to produce exactly 1 fuel? So a couple interesting things to note here is, let's see. So every reaction turns out some quantities of a specific input chemical into some quantity of an output chemical. That's the format here. So you have the requirements on the left, you have the output on the right. There's always only going to be one output. So a reaction is basically going to be n inputs and 1 output. And then also important to note is that every chemical is produced by exactly 1 reaction. This means that whenever you see a requirement, like in this case, we have this requirement for 7 A components, there's only one reaction or recipe that you're going to be able to run in order to make those components. So you don't need to like branch out and test different reactions to try and optimize here. And the only exception is ore, and ore is kind of like our base material, or raw material, as it says here, and is not produced by a reaction. So ore will never appear in the output section of our reactions here. But important to note is that every other chemical or ingredient does appear in the outputs of the reaction exactly 1 time. Cool. And the question is basically like, starting with fuel, if we satisfy all the if we run all the reactions to satisfy all the requirements for fuel, what is the total cost in ore that we've racked up? So yeah, that's problem 14. And as I was saying before, you could maybe you could make a tree or a directed acyclic graph with like fuel at the top and kind of you can do like a search to get down to ore. There's a bunch of different ways that you can tackle this. But as I mentioned in the intro, we will be going for the simplest possible solution. But first, as per usual, we need to parse our inputs. So we have P14 text. As the problem was telling you, this is our problem input, and each row is a reaction. So again, on the right, we have one input, and then each reaction has in number of, we have one output, and then each reaction has a number of inputs. And there's quite a few. This list is 0 indexed. Yep. So we have 63 reactions. Fuel will be in here somewhere, and then ore will be in here somewhere as well. All right. So parsing this is a little bit trickier than we've encountered in previous days. But basically, what I want to do here is we don't care about the special characters, so we don't care about white space, commas, equal sign, all this. Basically, we care about the quantity for each of the inputs and the outputs, and we care about the identifiers. Quantities will, of course, be digits, and then identifiers look like they are uppercase alphabetic. So yeah, as usual, we'll use inget to read our inputs. That separates it by row. Now what I'm going to do is, so in order to pull out the digits, we can use digit characters. In order to pull out the identifiers, we can use alphanumeric. APL gives you quad functions for these. So quad D, quad A gives you a list of all the characters in the digit set, as well as a list of all of the uppercase alphabetic characters. And if you put them together like this, this is called stranding notation, and this will give you two enclosed lists. So if I take our list of problem inputs and I do a Cartesian or an outer product, and we use a train here, we'll say, well, let's put so we have our digits and our alphanumeric character or alphabetic characters on the right. We have our problem inputs on the left. And we can parse these out using partitioned enclose, like so. And that will give us this. So each row here represents a reaction. And then on the left, we have all the quantities, and on the right, we have all the identifiers. And you can sort of spot check this. You can see 1, 11, 7, 1, 11, 7 here on the first row. JNDQ, pH, blah, blah, blah. These identifiers match up. If you are curious, I use this type of train a lot with partitioned enclose in order to pull out like characters that I care about. I've used it a lot in previous videos, but again, you can see an example of it if you just look at the sort of tooltip here for left shoe underbar. Here they're splitting on white space. Okay, great. So this is our problem input. We can assign this to P. And then what I'm going to need is a unique list of all the different chemicals that we expect to encounter. So for this, we can just take the rightmost column of our input matrix. And then what I'm going to do is for each one of these, I'm going to take the last element. So that is take reverse for each. And remember, so the last element here for these different identifiers, this is going to be the output. And remember that OR does not, it doesn't have a reaction in which is the output. So in order to get the full unique list, we need to add OR to it. Great, and the length of this should be, if we have 63 reactions, that means that we have 63 sort of chemicals that we can build, plus OR will give us 64. And we'll call this I for ingredients. So the important thing about I is that each index at I represents the index here of a reaction, and that will be the output for it. So oh, I actually want to put or at the end. I'm sorry. So let's look at I. So like our first reaction here, we can see that the output is LBJSB. And our second reaction here, we have BCGJ or JG. Yeah, so it's ordered like that. And then we put or at the end because it doesn't have a reaction that produces it. So that's going to kind of be our special case here. We're just adding it on the end so we have a list of all the different chemicals that we'll encounter. Cool. So if we look at P, now this problem is very important to think of the correct data structure that you want for your problem. Or in other words, how are you going to represent the data so that you can work on it? We're going to be using an array because this is APL. The question is just how do we want to structure that array? And what I think makes sense for this is I would like a matrix where the rows of the matrix will correspond to our different reactions, and the columns of the matrix will correspond to our different chemicals in terms of which ones we require. So for this, first row, this will be our first row in the matrix, and we have 1, 11, 7. So I want this row in the matrix to denote the fact that we require 1 J and DQ, we require 11 pH and C, and this reaction produces 7 LBJs. Now the trick is we have to differentiate somehow between the inputs and the output. And after thinking about this for a while, I think that it makes sense to denote requirements with negative numbers and outputs with positive numbers. The way that I kind of think about this is that when you run a reaction, you're producing something, that's your positive number, but you're also kind of incurring a debt. And that's what those negative numbers mean. Those negative numbers mean that you need to run another reaction in order to satisfy that debt. So in this case, we have a debt of 1 J and DQ. We have a debt of 11 of these pH and Cs, and we need to run those corresponding reactions in order to produce those in order to satisfy that debt. If this doesn't make sense, then I'm hoping it will shortly. So what I'm going to do is I am going to run a reduction on P. Reduce we're basically going to take a function and it will be placed between each pair of cells here for each row. So for this function, omega is going to be our identifiers on the right, and alpha will be our quantities on the left. So if we're putting together a matrix, the first thing that we want to do is we want to get a starting point, and we can use the new constant function introduced in Dyalog 18 to just start with a bunch of zeros. So for our rows in the matrix, 0 basically means that like the corresponding chemical is irrelevant to the reaction. It's, we don't care about it. So this says for each I, which remember is our list of unique chemicals or ingredients, just put in a 0. So if we do this, yeah, we just get a bunch of zeros. We mix this. We have a matrix full of zeros. Not very exciting yet. But what we want to do is now that we have sort of the shape of our matrix figured out, we want to insert our numbers at specific indices. And when we're inserting in specific indices, the at operator works really well for that. So where do we want to insert? Well, we can look up in I these outputs. So that'll be I index of omega, right? And that just gives us the indices in I where those identifiers occur. And now we just have to insert our quantities into those indices. So for the left-hand side, keep in mind that they are still strings, so we will need to convert them into numbers. So for each alpha executes, this gives us numbers. And then I'm going to negate all of them. And remember when I said that each of the inputs we're going to represent with negative numbers, and it's just the output, the last number in this list, that gets represented with a positive number. So if we negate all of them, that means that the only thing that we have to do is negate or absolute value the last item in the list in order to make it positive. So in APL, that would be, we can do something like reverse negate at 1 reverse. So this basically reverses the list, and then at the first element we're applying negate again, and then we're reversing to undo our first reverse. So this is negating all of the elements except for the last one, basically is what this translates to. And this will give us a bunch of enclosed rows. So if we mix it all together, we get this matrix. And let's see if I can make this a bit clearer. So if we put I on top as the column headers, and then if we do a -1 drop I, because we don't care about or, but we do need a empty string on the top. Yeah, how about this? Now this makes things a little bit clearer. So we have a matrix, and each row corresponds to the reaction that produces a specific chemical. So our first row produces LBJSB. It's the same order as our input here. The second row produces VCJGs. Same here. And the outputs are sort of placed here along the diagonals. These are all our positive numbers. And so you can see that the reaction for LBJSB produces 7 LBJSBs, which if you look at our input, that's correct. It also has a requirement, or we're incurring a debt, so that's why it's negative 11 pH and Cs. And then J and DQ is in here somewhere. There it is. -1 J and DQ. So that is, we basically parse this out. We've turned it into a matrix. I'm going to close this because we don't really need the problem input anymore. But the really nice thing about this layout is that the indices, you can see here I've just basically taken our list of unique ingredients, I, and I've laid it across the columns and I've laid it across the rows, and it's the same order. So that means, let's say that we're looking at a reaction for LBJSBs, and we know that we need, we need 11 of these pH and Cs, whatever. If we just find the index of this, the index of this -11 in the row is going to be equivalent to the index of the row that we need to run, because the identifiers are the same along the columns and the rows. So basically what we can do is, when we want to run a reaction, we can look at all of the negative numbers. We can get the indices for those, and if we index into this matrix and we pull out the rows, that gives us all the reactions that we need to run. So to make this a little bit more concrete, first of all, let's see. Let's actually assign this matrix to M. Yep, there's M. And then let's get our fuel reaction, because we're going to start from there. So we'll say FR equals M index ingredient list index of fuel. Right, and this is our fuel reaction. So if we, you can see here that we have some requirements. We don't really know the identifier of these, but it doesn't really matter because it's only the index that matters. And then somewhere in here should be a positive number. Yep, so we can see that this reaction produces 1 fuel. So let's write a function that operates on this fuel row. I would like tell me what the indices of the negative numbers of omega is minus the last row, because the last row, or the last the last item is going to be ore, and we don't have a reaction that produces ore, so it doesn't make sense to look for it. So if we do this, we can see that we have negative numbers at indices 8, 9, 14, 17, 27, etc. Okay, cool. Let's assign that to n, and then we can start doing some indexing. So we can say if we index into m our matrix, we can get all of the reactions that correspond to these indices. So let's assign this to R for reactions or recipes. And then if we index back into omega, it will actually give us the negative numbers themselves. So think of it as like filtering for all the negative numbers. So that'll be W index enclosed indices. We'll call this D for debts. These are kind of, like I mentioned before, I think of them as like debts that we need to satisfy. And then if we look at these, we can look at our reactions and our debts. So these negative numbers all represent like the quantity of the materials that we need in order to produce one fuel. And this matrix here, these are all rows out of our matrix that represent the reactions or the recipes that we can run in order to get those ingredients. So you can see here, we have a requirement for 12 of this first reaction. Now, this first reaction only produces one thing. You can see because it's the only positive number there. So we're going to need to run this reaction 12 times in order to satisfy this debt, right? And again, here you can see that we have a debt or a requirement for 28 of whatever this second reaction is. This second reaction produces 5 things. So we're going to need to run this second reaction 6 times, which will give us 30. That'll satisfy our requirement of 28, but we'll have a surplus of 2. So we're going to need to track that surplus. And again, this is where, when I was looking at other solutions, people came up with these elaborate schemes to track their surplus and stuff. But here it's going to be very simple, as we can see. So basically, we know that we need to run all of these reactions in order to satisfy our requirements for fuel. And the only question is how many times we run these reactions. And I kind of walked you through how we would do it. We basically take the requirements divided by the positive number here, or the number of materials that are produced by the reaction, and then you take the ceiling of that in order to like you can't do partial runs of the reaction. So you take the ceiling in order to make sure that you're satisfying all the requirements, and yes, there will be surplus, but we'll take care of that. So in order to get all of our, basically to get the outputs of these different reactions, we can just take the max reduce of the reactions. And because there's only a single positive number in each row that represents the outputs, just taking the max is going to return the outputs, as you can see here. So we have 1, 5, 9, 5. You can see where these appear in our reaction row. And then we take our debts divided by that amount. We get this, right? So all of our debts are going to be negative numbers, so we can take the absolute value of all of that, and we'll take the ceiling. And now we get these nice round numbers, which tells us how many times we need to run each reaction row. This is basically, like I was saying, like take this second requirement. We have a requirement for 28. The reaction produces 5. So as you can see here, we'll need to run it 6 times because you can't do partial runs of reactions. 6 times 5 is 30. That solves the requirement for this 28, but you'll have a surplus of 2. So in order to simulate running these reactions multiple times, we can just multiply the rows by the number of times that we need to run it. So that will be R multiply rank 1, 0. This is saying for each row in our reactions, multiply it by each number in our count here. That gives us this. So yeah, now our outputs are 12, 30, 18, etc., etc. You can see that this is enough to meet our requirements. So we can sum all of our rows down. This is sum reduce first axis. That'll give us this row of numbers. And then we can add our original row to this. The shapes are the same, in order to give us basically the sort of the state of the world after we've run all those reactions. So we have new requirements, or new debts that we've incurred as a result of running these reactions. We now also have positive numbers that indicate surplus of various materials. Let me, maybe I can make this clearer. Let's see. Put I as column headers, and then let's do fuel row, and then I can do before, after. Yeah, okay. So this this top row indicates our original fuel reaction, right? And we can see that our fuel reaction requires 12 FQM whatever, 28 GMV whatever, 15 BDZs. Now after doing this math and sort of running the reactions, you can see down here in the second row, we no longer have any negative numbers where there were negative numbers in the first row. Basically, we satisfied all of those requirements that we started out with, and we have some surplus in some cases, right? But now, as a result of running those reactions, we have new requirements that we need to satisfy. So like now we need to come up with 10 KSLFDs. We need to come up with 3 QBGs. We need 228 PHNCs. We have ore on the very right here. We haven't incurred any requirements for ore yet, but presumably that'll happen. So yeah, basically the way that this works is, we'll get in our requirements row. We look at all the negative numbers in that row. We know that we need to run reactions in order to satisfy those requirements. And then, we basically run all those reactions. We add it all together. We get new requirements. We get some surplus. And what we want to do is basically we just want to keep running this until we don't have any more negative numbers, right? If we don't have any negative numbers, that means we don't have any requirements and we're done. So we have the indices here on the far left. This n. N is the list of indices of negative numbers. So we can just say, if Zilda, or the empty list, is equal to our indices of negative numbers, this is basically saying if there aren't any negative numbers, then we'll take the rightmost argument of W and take the absolute value. So what I'm doing here is I'm saying, hey, if there aren't any negative numbers, we're done. The last element is equivalent to the amount of ore that was required. And so we're taking the last element and we're taking the absolute value because it's going to be a negative number. So this is basically just saying, like, when we're done, tell me how much ore we ended up using. And then all we have to do over here is we'll just say, otherwise, if there are negative numbers, recurse on the new row. That gives us this number, which is the number of ore that was required after we met all of our requirements recursively. So 114,125. And that is indeed the answer here. So, like, yeah, we didn't need We don't need trees, we don't need hash maps, we don't need any of this stuff. We're basically just determining what our requirements are by looking for negative numbers. We pull all of the reactions that we need to run. We run them all simultaneously, and then we evaluate our new requirements. I guess you can kind of think of this as like a breadth first search of the requirements tree, if you want. But the way that this is done with, like, all that we're doing is we're just indexing into a matrix, and then we're just doing some math. We're doing division, multiplication, addition. And then we're just using recursion, which in Dyalog supports tail call optimization. So because we don't have anything on the left side here, this is basically equivalent to a loop. So it's very fast. All right. Anyway, and we'll look at just how fast it is here in a minute. So now we say, after collecting ore for a while, you check your cargo hold. 1 trillion units of ore. This is 1 E12. Given 1 trillion ore, what is the maximum amount of fuel you can produce? So now this is kind of the inverse question. We have a function. Well, actually, we don't yet. So if I assign this to a function and I say, hey, instead of just starting with the fuel row, multiply the fuel row by some omega. Now we have a function that says, hey, given some amount of fuel, how much ore will it take? So we can run this for F1 fuel to get the same answer as before. We can run it for 10. We can, run it for the numbers from 1 to 10. Great, so we have a function that says, basically, given some amount of fuel, how much ore does it produce? And now we need to sort of go the opposite direction. So when I first solved this, I did sort of the naive approach, basically a binary search. Right, so in a binary search, we have we start with some lower bounds, some upper bounds, and then we basically bisect it. We look at the average, we test right there in the middle, and then depending on the results of that test, we'll either shorten our range to the upper half or the lower half. Right? So let's look at the binary search first. Binary search, first we need to determine what the upper bound is. So we can basically say if 1E12 is less than FW, then W, otherwise recurse on 2 times omega. This basically says start with 1, keep multiplying it by 2, so keep doubling until we get an ore count that's greater than 1 trillion. That gives us this. This is kind of our upper bound. So if we want to use that as our upper bound and we want to use 1 as our lower bound, the binary search would basically be like, so find the average of alpha plus omega. That's alpha plus omega divided by 2. And then floor it. We can assign this to A for average. And we're basically going to say if alpha is equal to that, then return A. Otherwise, if 1E12 is, what is this? If 1E12 is greater than FA, then we want to increase the range, right? So that'll be A recurse omega, or upper bound. Otherwise, we want to try the lower range, so it'll be alpha, or a lower bound, with the midpoint as our new upper bound. I think that's right. Yeah. So yeah, this is the binary search. We're basically, we establish an upper bound first, and then using 1 as our lower bound, we continually bisect, do some testing, until we find the correct answer, which is 120, 394, whatever. That is indeed the correct answer. My problem with this is that it is fairly slow, or we can do better. So if I load in compx and we time this, we can see that to run part 2 here takes E-3, this is 2.7 milliseconds, right? Which is actually pretty good. I saw, some C solutions that were taking 8 milliseconds, even some Rust solutions that were up there. So 2.7 milliseconds to run part 2 is pretty good already, but we can do better. The binary search algorithm is a little bit naive. There's a better way to do this, which is basically like, so if we look at our fuel cost for one, or if we look at our ore cost for one fuel, let's say that we try and extrapolate this out to the first 10 numbers, right? What's interesting is that as you produce more fuel, you're going to have more surplus that you're able to use. What that basically means is that the first unit of fuel that you produce is going to be the most expensive in terms of ore, because after you've produced that first fuel, now you have surplus that you can use. So as a way of demonstrating this, if we look at if instead of multiplying the cost for one fuel over the first 10 numbers, if we say run, tell me the exact cost in terms of ore for the first 10 numbers, you can see that there's a difference here, right? That first unit of fuel was the most expensive. And if you naively say, well, in order to produce 2 fuel, it's just double the cost, right? Well, it's not actually, because you have surplus that you can use, and so the cost is actually less. And the same keeps applying. If you're producing 3 fuel, well, now you have even more surplus that you can use, and so the cost is less yet again. What does this mean? This basically means if we determine the cost for the ore cost for producing 1 unit of fuel, then if we take 1 trillion and we divide it by that ore cost, that'll give us some like fuel count, and we know that we can produce at least that much fuel given that much ore. The actual cost is going to be, or the actual amount of fuel that we can produce is going to be more than that, because we're able to use surplus, but it gives us a lower bound. And that lower bound is going to be a lot more accurate than just doing a binary search. So in order to sort of formalize this a little bit, let's say that we start at 1, and I'm just going to say ore, tell us how much ore we need for our fuel count plus 1. And if 1e12 is less than that, then just return omega. Otherwise, take 1e12 divided by the ore cost. So the reason I'm using w plus 1 here is because we are sort of interested in, once we've identified the first occurrence where the ore cost is greater than 1 trillion, we want to step back 1 from that, because we want the greatest amount of fuel we can produce without going over 1 trillion. So, yep, and then floor that max omega plus 1 recurse. Yeah, and just to maybe let me do this. If I put a counter here and initialize it to 0, and then here in my binary search, I'm just going to say, well, we'll do this twice actually. So we'll increase our counter when we're finding the upper bound, and we'll increase our counter when we're actually executing the search. And then finally, I just want C. I don't care about the results. So as a result of both finding the upper bound and executing the binary search, we have called our function f. Basically, we've resolved our reactions 50 times. Right? Here, this solution, if I do this again, here we just run it 3 times. The answer is the same. So basically this heuristic of saying like, hey, if X fuel gives me Y ore, then if I take a trillion divided by Y, I know that I can get at least that much fuel out of it. And that's your lower bounds, right? Let's put this into even more stark terms. If I were to take this new way of doing things, and if I put it up against binary search, we can see that it is, what is this, almost 20 times faster? So the binary search takes 2.6 milliseconds. This new algorithm takes 160 microseconds, or 0.16 milliseconds. So with this new algorithm, and sort of the matrix way of resolving these requirements and doing the reactions, we are down to 160 microseconds for running part 2. Which is pretty good. I don't think that this is the flat out fastest solution I've seen. Someone posted like a Rust solution where it's maybe a bit faster than this, but they had to do like all sorts of optimization and they're worrying about data types and they're doing this and that. Basically, we tackled this problem by doing the simplest possible thing we could in APL, which is carefully putting our data into a matrix or an array, a single large one, right? So that when we work on it, we get all the benefits of contiguous memory access, caching, all that stuff. So all our reactions are in a big array, and then we solve our requirements at each step by just doing indexing and matrix math, which are extremely fast on vectorized CPUs. So yeah, I mean, if you sort of adapt to this way of thinking, first of all, your solution is going to be very simple. This whole thing is probably 4 lines, and it's going to be very quick if you structure things that way. And you don't really have to think about data types and all the rest of this because the primitives are already insanely quick. So anyway, I thought that this was kind of cool, and I wanted to share it. So as I mentioned before, I will return back to problem 12 because I think that that's another interesting problem for matrix-based solutions. It's basically, what is that one? That's the in-body problem. Yeah, so that one should be fun as well. Cool. Thanks for watching, and I'll see you next time.